Everyone, welcome to part 4 of chapter 9. This will wrap up chapter 9 for us. Here we go. So today we are going to talk about polar and non-polar bonds as like our first topic. So in the previous sets of slides, we've learned how to draw covalent molecules. And so when we draw these covalent molecules and draw their Lewis structures, we are looking at how the electrons are arranged in the atoms, right? Where are the electrons? Are they on the nitrogen? Are they on the oxygen, right? But we can also figure out whether the molecule itself is polar or non-polar. And this will tell us a lot about the properties of that molecule. And we are going to use this a lot, especially when we start looking at intermolecular forces. And like I've talked about a lot in this class, chemistry is a cumulative subject. So now that you know how to draw Lewis structures, now we can use it to figure out whether molecules are polar or non-polar. And then after that, we can use that, is it polar or non-polar to start determining, what type of intermolecular forces it has, and we can determine the properties, right? But it all goes back to you need to be able to draw really, really good Lewis structures. So make sure you're still practicing that and getting really good at that. So we have two different types of covalent bonds. We have polar bonds and we have non-polar bonds. So non-polar bonds occur between similar atoms. So like here in this molecule, we have two hydrogen atoms that are being bonded together. Since these atoms are identical, the electrons will be shared equally between these two atoms. So you can think of the electrons that are shared in that bond as just sitting right smack in the middle. They're not closer to one hydrogen or the other. They're being shared equally between those two hydrogens. So there you go. The electrons are shared equally between the two protons. When we have polar bonds, these are when we have different atoms or atoms with really different electronegativities. And then the electrons will not sit directly between the hydrogen and the fluorine. They're still going to be between them, but they're going to sit closer to one atom or the other. We get this charge separation is what we call it in the molecule. And this is due to the electronegativity. So since fluorine, we've talked a lot about fluorine. Fluorine is the most electronegative atom on the periodic table. And since fluorine is more electronegative than hydrogen, the electrons will actually sit closer rather than them being right in the middle. The electrons are going to sit closer to fluorine than they will to hydrogen because fluorine has a greater ability to pull those electrons towards it. It has a larger electronegativity. And when the electrons sit closer to fluorine, this gives fluorine a partial negative charge. Okay, and we write it like this because it's kind of looking like, and this is the Greek lowercase letter delta. So we know the Greek capital letter delta is a triangle, right, which means change. This is the Greek lowercase letter delta, and that means partial. And so since these electrons are sitting closer to fluorine than they are to hydrogen, it kind of acts like fluorine has, quote unquote, gained some electrons. And since fluorine has kind of gained some electrons, it gets this partial negative charge. And when the electrons are sitting closer to, since the electrons are sitting closer to fluorine than hydrogen, kind of feels like it has now lost some electrons, right? Because they're sitting closer to fluorine. So hydrogen will get a partial positive charge because it is essentially kind of lost some electrons. But again, these aren't full positive charge or full negative charges because the electrons haven't been transferred, right? We see the electron transfer in ionic compounds. But in covalent compounds, the electrons are just being shifted within this bond. So the electrons are shifted within the bond closer to fluorine because it's more electronegative. So fluorine will get that partial minus, like it's kind of gained electrons, and hydrogen will get a partial positive, like it's kind of lost electrons. And so this down here at the bottom, This shows the direction of the dipole moment, and it's always going to go from the partial positive atom to the partial negative atom. So the way that I do it is I put a plus sign at the positive, and then I finish my arrow toward the negative atom. Okay, so that arrow is showing the polarity of the bond or the polarity of the molecule, depending on which one you're looking at. So again, put the plus sign at the positive one, the plus sign at the hydrogen, and then finish your arrow toward the one with the partial minus, and that will show the direction of the dipole moment. So polar covalent bonds are when the electrons are unequally shared. And we'll determine this because there's an electronegativity difference, and it gives you this range, 0.3 to 1.7. And essentially, like these, there's a lot of variation in the cutoffs, which isn't awesome. But this is kind of like a rough estimate. So if you have, if it's below 0.3, it's, between 0 to 0.3, we're going to say that this is nonpolar. The electrons are being shared fairly equally, right? Maybe not perfectly equally, but at least, they have a similar electronegativities. But as soon as we get two atoms with a large difference in electronegativities, or at least fairly large difference, then the electrons in that bond will shift toward one atom or the other, and then we will get polar covalent bonds. This is when the electrons are not shared equally. Okay, so nonpolar, they're shared equally, similar electronegativities. Polar, they're not shared equally. We have a difference in electronegativities. If it is greater than an electronegativity difference of 1.7, if you have a really large difference in electronegativities, that anything greater than 1.7, that's going to be an ionic compound. And I'll reference that again later. So here's our table of electronegativities. And so this will be provided to you. We've referenced this quite a few times. And so if I need you to calculate, electronegativity differences, then I will give this to you. You will just need to know like the general cutoffs. Kind of a good rule of thumb though is usually if things are, close on the periodic table, then they're probably a really similar difference in electronegativities. If things are far apart on the, on the periodic table, then they probably have a larger difference in electronegativities, just as kind of a rule of thumb. When you're trying to figure out anything about hydrogen, if you're trying to use this like rule of thumb, hydrogen you can think of being as where phosphorus is. They have the same electronegativity. So if you're trying to use this like, is it close to things on the periodic table, just stick hydrogen where phosphorus is, and that'll give you, enough to go on. So if we were trying to determine, which of these bonds was the most polar, we would look at the difference in electronegativities. So since if we have two of the same atom, right, that's going to be very non-polar. Those electrons are going to sit directly between the two hydrogen atoms. And again, we can think of, hydrogen essentially as being where phosphorus is on the periodic table. Hydrogen to sulfur, right, we have 2.1 to 2.5. This is a 0.4 difference in electronegativities. And so, obviously that's going to be greater than 0.0. So this is slightly polar. We would classify it as a polar bond, but it's very, very slightly polar. Now, if we look at, chlorine to hydrogen, we have 2.1 to 3.0. That's a difference of 0.9. So we're getting more and more polar. Oxygen to hydrogen will be a difference of 1.4. And then fluorine to hydrogen will be a difference of 1.9. So again, we're just looking at the difference between the values. So if you're asked to rank them in terms of polarity, then this table would be provided for you. So here's our hydrogen molecule. So again, they have the same electronegativities, right? So our difference in electronegativity is 0. We would classify this as nonpolar covalent. If we have hydrogen chloride, right, we can look at their electronegativities, 2.1 to 3.0. This is an electronegativity difference of 0.9. So this one is polar covalent. And if we were to go through and assign the partial negatives and partial positives, which you'll usually do if I'm asking you about polarity, then we would look at, okay, which one of these is more electronegative? Chlorine is more electronegative than hydrogen is, which means that it will pull the electrons closer to the chlorine. So rather than sitting them directly in the middle, right, they're sitting closer to chlorine than they are to hydrogen. And so when this happens, then chlorine experiences a partial negative charge. Hydrogen will have a partial positive charge. And when we would draw the dipole moment, again, it's always going to go from the positive to the negative. So that would be the direction of the polarity, right? The direction of the dipole moment. Oh, there we go. They're going to fly in. All right. And then if we were going to look at sodium and chlorine and their electronegativities, right? They have a very large electronegativity difference. And we said that anything greater than 1.7, right? If it was greater than 1.7, we would classify this as ionic. So this is not a molecule, right? This is a compound. And we talked about last time or the time before, right? The word molecule is kind of exclusive for covalent bonds. So we say no molecule exists here because this is an ionic compound. But again, you likely could have recognized that without the difference in electronegativity because you know that sodium is a metal and chlorine is a nonmetal. And we know that when we have a metal and a nonmetal, that forms an ionic compound. And so the reason that they form an ionic compound is because this difference in electronegativity is so great that rather than chlorine just kind of pulling the electrons towards it, we get that big transfer of electrons. The electrons go from the sodium to the chlorine. Electrons are, lost and gained. And so now we have these complete positive and complete negative charges rather than the partial charges that we were talking about before. So this is just a little bit of a side topic about how these bonds form in general. So if we had, our two hydrogen atoms, so these are, here's one of them, here's another one. And they start off really far apart. And as they get closer and closer and closer together, right, they are going to experience, there we go. For part 2, they're going to experience some attraction to each other because they both have one valence electron. They would like to form a bond so that they can have two valence electrons. There's going to be this point, right? So this is going to be the energy absorbed, here, I'll talk about that in a second. There's going to be this point where they're going to find this happy place where these competing attractive and repulsive forces, which will fly in here in a minute, are kind of at an equilibrium of sorts. Okay, so if they're, if they get too close together though, then we get the protons in the middle that are repelling each other. They'll find this happy place here where we have these forces that are happening. Electron repulsive forces, right? So the electrons, the valence electrons and the valence electrons here are repelling each other, right? Because they're negative. And then we have the proton repelling forces here because they're positive. So they can't get too close together, right? They can't be too far apart. They can't be too close together. They're trying to, balance all of these different forces out. We also have electron-proton attractive forces, right? Because the electrons on, in one atom are attracted to the protons in the other. And so if we can find a place where we, minimize our proton-proton repulsive forces and our electron-electron repulsive forces and maximize our electron-proton attractive forces, then we'll get this, actual bond length, okay? More on this in, higher levels of chemistry and figuring out bond length. But we did talk about bond length before. This is just kind of how or why, some are, different than others. And so this particular bond length will correspond to a certain amount of energy. Okay, the energy is really what we're caring about in today's class. So we have, this value of energy here. I know that the arrows don't meet exactly, but, they're supposed to both come from here. They've just kind of shifted them left and right so you can see them both. So, but this negative 432 kilojoules per mole will be the energy released when the bond forms or the energy absorbed when we need to break this bond. But this bond length, like I said, corresponds to a certain amount of energy. We have lots of different bond energies, right? Here's a table. You have some more values at the end of your Chapter 9 lecture worksheet. So you're never going to have to be, memorizing these, and you won't probably use them enough to even, be able to recall them off the top of your head. This bond energy is technically defined as the standard enthalpy change for breaking a bond into 1 mole of gaseous molecules. This is technically defined as an endothermic process, right? Which is why these are all positive. Okay, it's determined by how much energy is needed to break the bond. But if you take the negative of that, that's the energy that will be released when the bond is formed. And more on that in a little bit. I did want to bring this to your attention again, that we talked about last time, that as we are increasing multiplicity, right, as we get more and more and more bonds, like going from the carbon-carbon single bond to the double bond to the triple bond, our bond length is getting shorter and shorter, and our bond energy, right, our bond strength essentially, is getting larger and larger. So more bonds, right, higher multiplicity will give you a shorter and stronger bond. So in this table back here, you'll also see that that's true. They're just kind of moved around. Like here's our carbon-carbon single bond, and our double bond, and our triple bond. They're just not all right in a row. But again, you can see that, as you increase in multiplicity, right, that bond energy is getting larger and larger and larger. So we can actually go through and calculate the amount of energy that's being released during a reaction using these bond energy values. And the way that we're going to do this is we are going to, right, so our energy that's being released or absorbed, that's our delta H of our reaction. That's our enthalpy of our reaction. And so it's going to be bonds broken minus bonds formed. That's the way that I remember this. The sum, all the bonds broken minus the sum of all the bonds formed. So we need the energy that you have to put in to break them, right? That's why this term is positive, because you need to input energy to break the bonds. And then this one, right, the reason that this negative sign here is because you need to, when the bonds are formed, energy is going to be released, which is negative, right, exothermic. So breaking bonds always requires energy. You have to input energy to break the bonds. And forming bonds will always release energy, because that's going to a more kind of stable configuration. Your reactants aren't as high energy now, so they're going to release some energy. So again, that's why it's always bonds broken minus bonds formed, because this needs to be positive, this needs to be negative, so we can figure out what our delta H of our reaction is. If we had to input more energy than we got out, that will be an endothermic reaction, because delta H of the reaction will end up positive. If we got out a ton of energy and only had to put in a little bit, then our delta H of the reaction will be negative, making it exothermic. So I'm going to go through some examples on how do we calculate that. So here's just kind of a general, kind of visual way of thinking about it. So let's say that these are our reactants. So during this reaction, the way that things react is they need to break the bonds that are holding them together. So we need to break this bond, we need to break this bond, and we need to break this bond. So in order to break those bonds, right, we have to input energy. That's going to be a positive value. And then we'll have all of our atoms broken all apart. Okay? Once they are broken all apart, now we can react them together. And we can, this is carbon. These are carbon monoxides and oxygen gas. So now we can take our carbons and our loose oxygens that we've got, and we can make carbon dioxide. So here we are. So bond forming, right? When we form the bonds, a bunch of energy is going to be released during this process. So that's why the arrow is going down. It's going to be a negative value. Okay, so overall, just looking at the arrows, we had to input, a small amount of energy relative to the large amount of energy that we are getting out. So overall, this delta H of the reaction will be negative. This is an exothermic reaction because we got out more energy than we put in. So let's try it with a real reaction here. So this is, use the bond energies to calculate delta H of the reaction of methane. So our balanced chemical equation, we would have methane plus 2O2 gives us carbon dioxide and 2 waters. Okay, so that's our balanced chemical reaction we've got going on. And I would, when you're doing these, these calculations, I would always draw out the Lewis structures. And I know that sounds silly. You're like, why would I draw them out? They're really simplistic because you need to count up how many of the bonds there are. And you need to know whether things are bonded with double bonds or single bonds. So like this is methane, this is CH4, right? And I would actually go through and draw this. And then these are oxygen gas, and they are held together by a double bond, which is a different value than, a single bond. So I would go through and actually draw these out every single time. I know it's adding an extra step to your calculations, but I would rather go slow and do them right rather than just kind of rush through them and get them wrong. So again, this is going to be an endothermic process. We need to input energy to break these bonds. And so when we do this, right, we are going to break 1, 2, 3, 4 carbon-hydrogen bonds, which is why, like I said, it's good to draw this out so that you can actually go through and count 1, 2, 3, 4. And I know it sounds silly, but otherwise you will miss bonds. So we're going to break 4 carbon-hydrogen bonds, and then we're going to break this oxygen-oxygen double bond twice because there are 2 O2s, right? So we have to break this one, this double bond, and this double bond. So the way that we calculate that, getting ahead of myself here. So we broke 4 carbon-hydrogen bonds. Be is just bond energy. So we have 4 times 413. That's a value that you can look up. It's back a couple slides, or, it's at the end of your Chapter 9 lecture worksheet. And then we need to break 2 oxygen-oxygen double bonds. So be careful, like I said, that you recognize that this is a double bond and not a single bond, because this value is different for the single bond. It would be lower, right? It takes more energy to break a double bond than it does it takes more energy to break a double bond than it does a single bond. And we are breaking 2 of them because there are 2 oxygen molecules. So then we multiply those out, we add them together. That is how much energy we need to put in order to break these atoms apart. So now we've got them all loose and we can bond them together. So we're going to make 2 carbon dioxides and 2 waters. So there they are. Again, I would draw these out so that you make sure, right? We're making 1 carbon dioxide and 2 waters. But I would draw them out so you make sure that you can see that carbon dioxide is double bonded. Otherwise, these ones are probably familiar to you and you'd recognize that anyway. But on more complex molecules, you may not. So it's always helpful to draw the Lewis structure. So when we do this, we are going to break we're going to form 2 carbon-oxygen double bonds and 4 oxygen-hydrogen single bonds because there are 2 waters. And in each water, we have 2 oxygen-hydrogen bonds. So we need to form 1, 2, 3, 4. Again, I know it sounds silly to draw these out, but then you can actually go through and count them and make sure you haven't missed anything. So we are going to form 2 carbon-oxygen double bonds, right? Which again has a higher value than the single bonds. And then we are going to form 4 oxygen-hydrogen single bonds. So make sure, you've multiplied 2 waters and there's 2 of them in each one. And then you can add all of those up. So the way that we calculate our delta H of the reaction, we do bonds broken minus bonds formed. So here we are. Bonds broken minus bonds formed will give us 800. Oh, there should be a negative there. sorry, let me add this negative 818 kilojoules. That's how much energy will be released during this reaction. Since more energy was released during the bond formation than we had to put in to break the bonds, this is an exothermic reaction. So let's try this. Here's one. Calculate the change in enthalpy for the reaction below. So it says the bond energies are on the last page of your lecture worksheet packet. So if you don't have that in front of you, go ahead and grab it and then try to calculate this enthalpy. I will calculate it on the next slide in just a minute. Go ahead and pause. All right, so like I said, the first thing I would always do is draw out your molecule. So here we go. This is the first one. So C2H4 plus H2 gives us C2H6. All right, so now again, we need to do bonds broken minus bonds formed. And so we will have four carbon-hydrogen single bonds. 1, 2, 3, 4 that we need to break. And so if we look over at our paper, carbon-hydrogen single bonds are not on there. Hang on. They are 413 kilojoules per mole. Sorry, guys. And then we also need to break one carbon-carbon double bond. And so that value, sorry, I'm looking this up as I go as well, is 614. Then we also need to break this hydrogen-hydrogen single bond. And so that is going to be 432. So we're going to add up all of these. And then we are going to subtract all of the bonds that are going to form. So we're going to form one carbon-carbon single bond, which is 347. And we are also going to form 6 carbon-hydrogen single bonds, which are 6 times 413. So if we go through and calculate this, so I'm going to calculate it with you. So 1652 plus 614 plus 432 minus 347 plus 6 times 413. So that will get you that. So we can go 1652 plus 614 plus 432. That gets us 2698 minus 347 plus 2478 gets us 2825. So when we subtract those, we get negative 127 kilojoules. So this is an exothermic reaction because our delta H of our reaction came out negative. Let's go ahead and try another one. Same process, but go through and calculate the enthalpy of this reaction. All right, let's try this out. So again, I would draw these out. So we have ammonia and we have O2 and then we have 4 nitrogen dioxide. So when you're drawing these, always make sure that you've drawn, the Lewis structure correctly, or this will, impact, how you've calculated it. Okay. So nitrogen dioxide whoop, sorry everybody. Plus and this is a radical, sorry, there should only be one little electron there. But it's not going to impact our number of bonds. So when we go through, we are going to calculate this, and we have in this ammonia, right, there are 4 ammonias, and in each ammonia, we have 3 nitrogen-hydrogen bonds, okay? So there's going to be 12 nitrogen-hydrogen bonds total, okay? And the value of that nitrogen-hydrogen bond is 391. And then we need to break the oxygen-oxygen double bond, and its value is 495. So those are bonds broken. Sorry, and there are 7 of those. Minus bonds formed. So in this nitrogen dioxide, right, we have a double bond and a single bond. And we've talked about before, when we look at like resonance structures and things like that, they're not really a double bond and a single bond, but for this calculation, we're going to treat one of them as a double bond and one of them as a single bond. It's going to get us close to that right answer. So we have bonds broken minus bonds formed. So we're going to break 4 nitrogen-oxygen double bonds, because there's a 4 here, and 4 nitrogen-oxygen single bonds. So 4 nitrogen-oxygen double bonds. And that is also not at the end of your lecture worksheet. Sorry, guys. Let's see if I can find it here. Nitrogen-oxygen double bonds are 607. And 4 nitrogen-oxygen single bonds, we have 201. And then we are going to break 6 waters. And in each water, I know it's kind of drawn, it's hard to see. In each water, we have 2 oxygen-hydrogen single bonds. So total, we are going to break 12 oxygen-hydrogen single bonds. So that value, we get 467. All right, so now we can go through, calculate these. 12 times 391 gets us 4692 plus 7 times 495. And then we are going to subtract out all of this stuff, right? All of our bonds formed. 4 times 607. All right, and then we can go through, wrap things up. And we get 45 kilojoules. And so this is an endothermic reaction because our delta H of the reaction came out positive. And that's the end. That's the end of this set of slides. So today we talked about polarity, and we talked about how to calculate the enthalpy of the reaction. This is actually the end of Chapter 9. So go through, finish up that Chapter 9 lecture worksheet. Make sure you know how to do, every single problem in Chapter 9. This will be the last chapter before the upcoming test. So please go through and do them, study hard, and as always, send me any questions you have.